Assalamu alaikum and very good morning, everyone. Welcome back to CHM 577, and this is my lecture number 14 entitled Metallic Bonding, Band Theory of Metals and Semiconductors. Prepared by Dr. Amalina, the notes, and then I'm presenting it for my students. For this lecture, the content will be metallic bondings, metallic properties, or properties of metals, Electron Sea or Electron Cloud Model, band theory of metals, and a little bit about semiconductors. And of course, when we are talking about metals, they have very specific place at which they exist in the periodic table, and they are practically these elements, the ones colored deep purple in this periodic table. These are all the metals in the on Earth that have been discovered and have been properly assigned in the periodic table. Typically on the right-hand side of the periodic table, and the ones on the typically on the left-hand side of the periodic table. Yeah, these ones on the left. Yeah, and the ones on the right, they are the non-metals, and anything in between, which is the boron, the silicon, the germanium, arsenic, stibbium, tellurium, astatine, these are called the metalloids. These are the elements that exist between the metals and the non-metals. Yeah. So those are really very basic knowledge of chemistry that everybody should know by now. And when we talk about metallic bondings, we have to look at a few theories. Yeah, metals, they consist of atoms that are tightly packed together in a giant lattice, similar to the lattice in ionic compounds. So if you can recall my lecture in the ionic, how you calculate the atoms in ions. So similarly like that, these atoms are tightly packed, but the outer electrons, if you can recall for metals, they have the outer electrons in the s orbitals and the d orbitals. Those with the outer electrons in the p orbitals are typically non-metals, but there are some exceptions. Now, the outer electrons or the valence electrons separate from their atoms and become delocalized, creating a sea of electrons. So if you can recall, you have the nucleus in the middle, and you have the orbitals, the shells, the first shell, the second shell, the third shell, and those electrons living on the outermost shells, you call them valence electrons. So when these atoms that are packed together make up a crystal, yeah, a crystalline situation, the outer electrons or the valence electrons can dissociate from the atom, and those outer electrons are free to move around the remaining ions. Yeah, obviously when the valence electrons leave, what remains of the atom is no longer a neutral entity. They are positively charged entities, which are called the anions. Yeah, the atoms become positive ions, and they are attracted to the valence electrons that have freed themselves, that have become the sea of electrons around the positively charged ions in the middle. So the attraction between the positively charged ions and the sea of electrons, or the cloud of electrons, or the delocalized electrons, this attraction between the positively charged ions and the negatively charged delocalized electrons, they are called metallic bonding. So remember, metallic bonding is, or the metallic bond is the bond that is made up, that is created due to the attraction between the positively charged ions and the negatively charged electrons that are swimming around the positively charged ions. So those are the metallic bond. So you get metallic bonding in the crystals of metals, that, and those metallic bonding that you see, those are very, very strong bonds as well. Yeah. Now, metallic bonds typically, as I was explaining earlier, form between atoms and metallic elements, between the atoms of metallic elements. The electron cloud around the atoms, that they arise from the sea of donated valence electrons or separated valence electrons, either one valence electrons for the first group, two valence electrons for the second group, or three valence electrons for the third group, and so on and so forth. So making metal good conductors at all states. Yeah. This metallic bond, they make metals very, very good conductors, either at solid state or at liquid state. They are very, very good conductors. Conductor of heat, conductor of electricity. This metallic bond also make the metal lustrous. Lustrous means they shine. They have some kind of luster, some kind of dull shine to it. So the example is sodium, iron, aluminium, gold, and cobalt. So this is probably time for me to show my lustrous iron. There you go, lustrous, sorry, gold, pulut dakap, that is. Yeah, so can you see the luster of this metal? Not that I want to show off, but that is just the example that I have at hand. Pardon the pun. Now, the attractive force between the electron cloud and the positive ions, that is called the metallic bond. So as you can see here, when you have a lot of sodium atoms packed together like this in this picture, the valence electrons will become free. What remains is the positively charged sodium, and the attraction between this positively charged sodium and the negatively charged electrons, it's the what is called the metallic bond. And the metallic bond makes your metal lustrous. It has luster, it has shine, because you see the electrons are freely moving within the structure of the metal. So, and that movement of electrons is what catches this the light and give it a shine, right? It also, the metallic bonds also make your metals good conductors of heat and electricity. I'm going to go through that a little bit later with you. So this is the properties of metal. Now, metal ions form a lattice which is more tightly packed and denser than the lattices in ionic compounds. They form crystals called, they form crystals which are called grains. And metals generally have very, very high melting point, very high boiling point, except for some metals, soft metals, for example, mercury, sodium, those are soft metals. Those are the exceptions. So the other metals are typically high melting point and high boiling point. Because metallic bonds are very strong, and a large amount of energy is needed to break that metallic bonds. Now, metals are good conductors of heat. The free electrons can take in heat energy, which makes them move faster. They can then transfer the energy throughout the lattice. Metals are also good electrical conductor. The free electrons can carry an electrical charge. Yeah, the free electrons can take heat, make them good heat conductor. The free electrons also can carry electric charge, making metals good electrical conductor. Silver is the best conductor of electricity, and copper is the second best. But why is copper being used a lot instead of silver for electrical wires? And this answer is actually economics, the cost. It is a lot more expensive to um, to uh, to mine silver. It is a little bit cheaper to get copper from the earth. Obviously, the earth contains all sorts of ores, and the ores are dug, and then the process of getting the pure metal from the ores. So it is a lot cheaper because because copper is a lot more abundant than silver on the crust of the earth. Yeah. So that is why silver is not being used as wiring. It's going to be very, very expensive. Yeah. Also, for the properties of metals, I'm going to talk about the strength. Metals are usually tough, usually strong, and they are not brittle. Brittle means they break easily like glass. So metals do not break easily. They are usually very tough. So when a metal is being hit by a hammer, for example, the layers of the lattice just slide over each other. They just slide. They don't break. They just, after force is being subjected to the metal, the atoms in the lattice just slide over one another. They just change the form. They do not break. So that is the property of metal. The metallic bonds do not break because the electrons that are making the metal bonds, they are free to move. Yeah, the electrons are free to move, making them easily to slide across one layer on top of another. So if you apply a force onto a lattice of metal, that metal is simply going um, to bend. That is the property that is called malleable. Malleable means they can be bent, they can be pressed into shape. Ductile means that they can be drawn, they can be pulled out to make them into wires. That is because the electrons, the sea of electrons or the cloud of electrons that surround the positively charged ions of metals are free to move around the lattice. So that metallic bonds give strength, give malleability, give ductility to the metal. So when we talk about metal grains, layers of atoms can slip over each other in metal grain when a force is applied. But this slippage stops at grain boundaries. So if you look into the crystal of metal under the microscope, you are going to see some areas which are distinctly separated from other area, and that is called grain. And this grain is actually what stops the slipping of atoms to continuously occur. Yeah. So if you using proper microscope, you are going to see that these grains occur. These are the areas at which the grains are occurring, where one grain meets one another. So you have the boundary between the grains, and within the grain you have the atoms. Okay, the smaller the grains, the shorter the distance the atoms, the atomic layers can move. So if you have the grain to be small, the ductility, the malleability of that metal is going to be short or to be low. But if the grain is big, then you have a more malleable or more ductile metal. This means that metals with smaller grains are stronger and harder than metals with larger grains. Is the property, the hardness of the metals is determined by the size of the grain. The faster the molten metal is cooled, the smaller the grain size. So the size of the grain depends on the rate at which a melted metal is being cooled. The quick cooling will produce smaller grain, and slow cooling will produce larger grain. So smaller grain will give you uh, uh, stronger and harder metals, but uh, bigger grain will give you a little bit softer metal. Yeah? How to strengthen metals? Because we use metals in our daily life to make our life much easier. Yeah. So metals can be made stronger. There are ways at which you can make your metal stronger. You can add another element when the metal is molten. You have, for example, a molten iron. You want to make that iron stronger when it cools. So you put other things in it. You can put another metal. You can also put another non-metal, typically a carbon. So you can put a little bit of carbon in your molten iron. Then the property of the steel, so steel is actually iron with carbon, is going to become stronger. Now the atoms of new elements spread through the crystal structure. So you have these atoms spreading through the crystal structure of the metal, making that metal stronger. Because the atoms of the added elements are larger, they make it difficult for the layers of the metal atom to slide. It's like a stopper. So when the metal is being hit by something, or by a hammer, for example, the presence of this big dopant, yeah, you dope or you add other metal to it, will prevent sliding and making that metal harder. It makes the metal less malleable and less ductile. This process is called alloying, and the new substance that is produced is called alloys. Now, you have to be careful with this term alloy. Strictly by definition, alloys are a mixture of one metal with a little bit of other metals in it. But the exception is with steel. Because iron, when you add a non-metal, which is carbon, you can also make something stronger. But sometimes, through this definition, carbon being non-metals, then you cannot call steel an alloy, strictly speaking. However, there are certain steel that contains other dopant, for example, chromium. So chromium with iron with carbon make an alloy. But if iron with carbon only, that's strictly speaking is not an alloy, because carbon is a non-metal. Because alloy is a mixture of metals, two different metals minimum. Yeah. So there is a question, there are a few questions here for you to answer, true or false. Metallic bonding is attraction between metal ions. Is that correct? It's not correct. Why? Try to find the answer yourself. All metals contain delocalized electrons. Is that true or false, according to what I have described to you earlier? Number 3, metallic bonds enable metals to be bent. Is that true or false? All metals conduct electricity and heat. True or false? All metals are solid at room temperature. Is it true or is it false? An alloy always contains two metals, at least. True or false? So please discuss among yourself the answer of these very, very simple questions. I'm going to move next to the Electron Sea or Electron Cloud Model. Now, the simplest way of explaining metallic bond is by assuming that the metallic lattice is composed of closely packed positive ions of metals surrounded by an electron sea or an electron cloud, as I explained earlier. This happens when metal atoms lose their valence electrons, forming metal cations, and the valence electrons then made up the electron sea or electron cloud. So metallic bonding involves the lattice of positive ions surrounded by delocalized electrons. This is what I have explained to you earlier. Metal atoms achieve stability by offloading or removing electrons to attain the electronic structure of the nearest noble gas. These valence electrons that have been offloaded join up to form a mobile cloud, which prevents the newly formed positive ions from flying apart due to the repulsion between the similar charges of the similar cations. So here is a picture of atoms arranged in regular close-packed three-dimensional crystal lattice. And this is the picture of the outer shell electrons or the valence electrons when they leave each of the atom to join the mobile cloud or sea of electrons that can roam through the metal, and the electron cloud binds the newly formed positive ions together through the metallic bonding. Now, the metallic bond strength depends on the number of outer electrons donated to the cloud and also depends on the size of the metal atom or the ion. For example, sodium. Sodium is a soft ion. It's a soft metal. Sorry, sodium is a soft metal. I'm sure you have done a little bit of experiment on cutting sodium and releasing it into water, maybe a few years ago when you were at school. Now, the strength of the metallic bonding in sodium is relatively weak because each atom donates only one electron to the cloud. Why one electron? Because sodium only has one valence electrons. Potassium, K. The metallic bond is weaker than sodium because the resulting ion is larger and the electron cloud has a bigger volume to cover. So it is less effective at holding the ions together. So sodium is softer than, potassium is softer than sodium, even though both potassium and sodium both have one valence electrons, but potassium being bigger and sodium being smaller make sodium a little bit harder or having stronger metallic bond than sodium because of the bigger volume for the electron cloud to cover and making it less effective. Yeah, but magnesium is definitely a harder metal than sodium and potassium. Why? Because each magnesium atom will release two electrons into the electron cloud. So there are more electrons in the electron cloud of magnesium. So in that same argument, aluminium, which is in group 3, will be a lot harder than magnesium because each one aluminium atom will donate 3 electrons to the electron cloud, making aluminium having very, very strong metallic bond. Okay. The strength of the metallic bond is inversely proportional to the size of the ion. Inversely proportional means the smaller the ion, the stronger the metal. The stronger the metallic bond and the obviously harder the metal. And it is directly proportional to the number of valence electrons. It is inversely proportional to the size, but it is directly proportional to the number of valence electrons in the metal. The smaller the size of the cation, the more electrons supplied, and the more electrons supplied by the electron cloud will contribute to the strength of the metallic bond. The stronger is the attractive force between the positively charged ion and the electron cloud, the stronger is the metallic bond that is formed. So across the periodic table, when you move from group 1 to group 2, 3, 4, 5, and so on and so forth, there is an increase in the strength of the metallic bond. So as you move from the left-hand side of periodic table, you are going to find harder and stronger metal, yeah, because of the uh, number of valence electrons and also because of the size, right? The strength of metallic bond, each sodium atom loses 1 valence electrons to build the electron cloud, forming 1 sodium plus. Magnesium and aluminium each will release 2 and 3 valence electrons, forming 2 Mg2 plus or Al3 plus, respectively. The more electrons swimming in the electron sea or in the electron cloud, the stronger is the attractive force between the electron cloud and increasingly positively charged metal ions. Therefore, the stronger the metallic bond. This is really a very, very simple concept. As the strength of the metallic bond increases, the values of the physical properties, such as the melting point, the boiling point, the hardness, will also increase, yeah, because the stronger the metallic bond, the stronger these properties will be, okay? Now let's go into the next theory. Previously, I was telling you about the theory of electron cloud or electron sea model. Now we go into the band theory of metal. Now metals are also described as having luster, yeah, the shine, yeah, so shine, good thermal and electrical conductivity, and they also are very malleable. These have been described a lot earlier. The properties are the direct results of the ability of the atoms to contribute electrons to a common cloud around the atoms. These facts indicate that the bonding in most metals is both strong and non-directional. The mobile electrons can conduct electricity and heat, and this is from the Electron Sea model. But that is on the Electron Sea model. I want to explain to you about the band theory of metals. Now, a related model that gives a more detailed view of the electron energies and motion is the band model, or sometimes known as the molecular orbital model. When two atomic orbitals interact, yeah, when you have two atoms, yeah, one atom here, one atom there, each one of the atom will have its own orbitals. It has the s orbitals, the p orbitals, the d orbitals. Yeah, this is not something new. So when these two atoms interact, they are going to produce. This is from the molecular orbital theory. They are going to produce what is called the bonding molecular orbital and anti-bonding molecular orbital. Yeah, this is the atomic orbital of metal A. This is the atomic orbital of metal B. When this A and B approach one another, the orbitals are going to interact, and these orbitals are going to make molecular orbitals. The atomic orbitals will make molecular orbitals, and there are two types of molecular orbitals for each interaction. One is called the bonding molecular orbital, which has a lower energy level, and another one is called the anti-bonding molecular orbital, which is higher energy level than the atomic orbitals. So that is the molecular orbital theory. You are going to meet with this molecular orbital theory in the next code of inorganic chemistry. So this is your first introduction to molecular orbital theory. Oh no, not next code, maybe the next topic in this code as well. Now, the band theory of metals, when many metal atoms interact, as in the metal crystal lattice, a large number of resulting molecular orbitals become more closely spaced, and finally, they will form a virtual continuum of levels called band. So this is really very, very simple and very, very easy to understand. When you have many, 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 many bands, but uh, uh, packed together, the many, many orbitals packed together, they are going to make a continuous band, just like your kayu lidi, for example, lidi kelapa. You have one lidi, you have two lidi, you have three, four, five, hundreds of lidi. It's going to make a big stick. So it's like this. So when you have one orbital, another orbital, and there are many, many hundreds and thousands and tens of thousands and millions of orbitals like this packed together, they are going to make a continuous band. So this is what's called the band theory of metals. Magnesium lattice, in the magnesium lattice, the number of atoms in even a small piece of magnesium is very large, in the order of 10 to the power of 20 metals. What is 10 to the power of 20? Now, 10 to the power of 6 is a million metal. 10 to the power of 7 is 10 million atomic metals. Metal atoms. And 10 to the power of 9 is 1,000 million or a billion. So 10 to the power of 20 is something big. So if you have many of these orbitals packed together, they're going to make a band. They're going to make a continuous band. Therefore, the number of molecular orbitals they form is also very large. Each magnesium atom has two valence electrons in the 3s orbitals, and the 3p orbitals are empty, obviously. Everybody knows that magnesium is 2s2. Yeah? 2p0. When many of these orbitals interact, two types of bands can be formed. So let's have a look. You have the valence band, which is the band which is full with electrons. And you also have another band which is called conduction band. And this conduction band are empty energy levels. So the valence band, full with electrons. For example, you have um, a parking lot full of cars. Yeah, a parking lot with many, 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 many cars. And then next to that parking lot, you have an empty road. You call the conduction band. So when these cars have access to when these cars in the parking lot have access to the road, then the cars can move. So similarly with electrons, when the electrons in the valence band have access to the empty conduction band, then the electrons can move. So when the electrons can move, so that can make a good electrical conductor. So for example, this conduction band is formed by the overlapping of the empty 3p orbitals, and for magnesium, the valence band is made up of the filled 3s orbital. Yeah, if you can recall your magnesium. So what is the periodic table? Let me see, somewhere here. That's the periodic table there. Yeah, magnesium is there. It's 3s2, 3s2, 3p0. So the valence band in magnesium is a combination of many, many 3s orbitals together that is full with electrons. It makes a valence band, which is the parking lot, the car parking lot that I was describing. But the conduction band is made up of the empty p orbitals in magnesium, and the empty orbitals is the road that will allow these cars to move. Yeah. So empty energy levels are called the conduction band. Filled energy levels are called the valence band. So here it is. You have many 3s's make a band like that, this purple band. Many 3p's make the empty conduction band. So 3s band is full with electrons, which is called the valence band. The 3p band is empty of electrons, and these are called the conduction band. There you are. You have the conduction band up here empty. You have the valence band full. And because the s and the p orbitals in magnesium, they overlap, there is no gap between the two, it is very easy for the electrons in the valence band to move to the, to move to the conduction band. When it is very easy for the electrons to move to the conduction band, then you can say that this particular substance is conducting electricity. Yep. Now, band theory of metals will explain three categories of material. You have the categories of insulator, which cannot conduct electricity. You have the category of conductor, which can conduct electricity easily. And you also have something in between called the semiconductor. Yeah. So what is the difference between an insulator, a semiconductor, and a conductor in terms of the band gap? If there is a large energy gap between the valence band and the conduction band, then the material is called an insulator, a large one. So the electrons in the valence band doesn't have energy to jump from the valence band to the conduction band. So it's impossible. And usually this will occur among the non-metals. If there is effectively no gap between the bands, the materials are called conductors, like the metal. But if the gap is finite but small, when the gap between the valence band and the conduction band is small, it is a gap, but it is small, the electrons from this valence band will have enough energy under circumstances to jump into the conduction band. And under these circumstances, you are going to have the material conducting electricity. But under different circumstances, it cannot. So it is called a semiconductor. Now it conducts, now it doesn't. Now it conducts, now it doesn't. So you have a semiconductor. And semiconductor is when you have a very small gap. We have a small gap between the valence band and conduction band. So conductors are mostly metals, insulators are mostly non-metals, semiconductors are metalloids. Metalloids, if you can recall what I explained earlier here, metalloids are these elements that sit in the border between your metals, which are down here, and your non-metals, which are up here. This boron, silicon, arsenic, tellurium, astatine, those are your metalloids. Yeah. So this is the band gap, big band gap between the valence band and the conduction band of an insulator. This is a small gap between the valence band and the conduction band of a semiconductor. And this is no gap between the valence band and the conduction band of a conductor. So this is the comparison of energy gaps between the valence band and conduction band in a metal. This is a metal, a semiconductor, and an insulator. Yeah. And the difference between semiconductor and insulator is really due to how big or how small is the band gap. If the band gap is smaller than 3 electron volt or 400 nanometers, then that material can be classified as a semiconductor. Electrons will have enough energy to jump the gap of smaller than 3 electron volt. But if the band gap is bigger than 3 electron volt or bigger than 400 nanometers like this, then you have an insulator. This large one, bigger than 400 nanometers or bigger than 3 electron volt, will disallow or will prevent electrons from the valence band to jump onto the conduction band, therefore cannot conduct electricity or become an insulator. The overlapping of empty or full bands also give metallic behavior. For example, you consider calcium. Calcium should have a full 4s band and empty 4p band. If they did not overlap, then calcium will not be a conductor. So the fact of calcium is a good electrical conductor give us an information that there is no gap between the 4s and the 4p bands of calcium. So electrical conductivity occurs when you have no gap between the valence band and the conduction band. Yeah, your electron is free to move between this field level to that empty level and move around. Yeah, electrons can go. Metal conductivity, metal, when you heat it, you are going to have a decrease in electrical conductivity. This is contrary to what we expect. We expect when something is heated, it's going to release more electrons or have energy to release more electrons. We would expect that the electrical conductivity of metal will increase with temperature, with electron promotion. But this is not what happens. That is because in conductor, there is no energy gap between the valence band and conduction band. You do not have to have any energy to promote the electrons from this valence band to that conduction band. It's just simply a very, very easy effort for electrons to just go to the conduction band. So it doesn't require any energy. Any energy that is provided into the metal will only act as a hindrance. Yeah, ability of electrons to travel smoothly through the solid in a conduction band depends on the uniformity of atom arrangement. An atom vibrating vigorously at high temperature is equivalent to an impurity, and it will disrupt the orbital. Therefore, with the disruption of the orbital, the disruption of the uniformity of the atom arrangement, electrons will not be able to flow freely. Therefore, for conductors, higher temperature means lower conductivity, lower electron conductivity. Okay? But the opposite is true for semiconductors or for metalloids. Low electrical conductivity for metalloids is found at room temperature. Higher electrical conductivity is at higher temperature. Electrical conductivity for semiconductors is found to increase with temperature. Why is this different? Why is the story different? It is simply because for semiconductors to conduct electricity, there is a gap of energy that is required to be crossed. Yeah, electrons have to cross between the valence band to the conduction band through a gap of energy. The more energy is provided, the more electrons will be able to jump across, and the more conductive the material will be. the gap between the valence and conduction is intermediate in size, jumpable, can be jumped. Higher temperature will provide more energy to allow more electrons to jump over to the conduction band, hence increased conductivity. Semiconducting elements from the basis of form the basis of solid-state electronic devices. So metalloids such as silicon or germanium are semiconducting elements whose electrical conductivity will increase as it is heated as the temperature increases. A striking property of these elements is that the conductivity is also markedly increased when they are doped, when a kind of impurity is introduced into it. So we are going to see how the conductivity of a semiconductor is increased through dopant. Okay. Semiconducting elements form the basis of solid-state electronic devices. For example, silicon, when it is doped with phosphorus, it will become an N-type semiconductor in which electrical current is carried by electrons. I'm going to explain to you later what this means. But when silicon is doped with boron, it becomes a P-type semiconductor in which an electrical current is carried by a positively charged holes. So what does that mean? So let's go through silicon. When you have silicon, each silicon has 4 valence electrons because silicon is just underneath. Yeah. What is it? Yep. There you go. Yeah. Silicon is just underneath carbon. Yeah. And silicon, like carbon, has P4. That means, no, P2, excuse me. S2P, S2P2. So there are 4 valence electrons in silicon. So having 4 valence electrons, silicon uses the valence electrons to make 4 covalent bonds to neighboring silicon atoms in the diamond-like structure. Yeah, silicon atom. So this is silicon. But, and in this case, you are going to have the valence band and the conduction band to be separated by 1.1 electron volt. Remember what is the formula? If the gap is less than 3 electron volt, then that material is semiconducting. So for silicon, it has 1.1 electron volt band gap, making silicon itself to be semiconducting. However, how do you increase or how do you enhance the conductivity of silicon? There are 2 ways. The first way is by introducing an element that will provide extra electrons. For example, you dope it or you put a little bit of arsenic. You put a little bit of arsenic into your silicon. Yeah, you put a little bit of arsenic into the silicon here. If you can recall previously, one silicon is bonded to 4 other silicons. One silicon in the middle bonded to 1, 2, 3, and 4 silicons. But when a little bit of arsenic is introduced into your silicon, for example, this arsenic, it is still bonded to 4 silicon. However, this arsenic coming from group 5, it is S2P3. Unlike silicon, which is S2P2. So when you have S2P3, there is 1 extra electron here at arsenic. And this extra electron is excess. It doesn't have anywhere to go. In an N-type doping, arsenic or phosphorus is added in small quantities to silicon. Both of these elements, arsenic or phosphorus, have 5 electrons in their outer orbitals, and they are not out of place when they get into the silicon crystalline structure. Since the 5th electron has nothing to bond with, it is free to move around. And it is this free to move around electron that will allow electrical current to flow through silicon in the N-type semiconductor. N means negative, negatively charged, because there is an excess electron, and each electron is negative. Yeah, it carries a negative charge. So N-type stands for negative type semiconductor, and the enhancement of the conductivity is because of the presence of the excess electron, and the carriers or the charge carrier are the electrons, negatively charged. And as you can see here, because it is extra electrons, you have donor level. You say here the Fermi level, or EF. You're going to have just a little bit of energy, a little bit more, a lot less than 1.1 electron volt of electron to move into the conduction band, making it a lot easier for that material to conduct electricity. Yeah. So you have the extra electrons here just sitting very, very close to the conduction band, easy for it to move and conduct electricity. So that is the N-type, the easily understandable type. What is the second type? The second type is called the P-type, or the positive type. And how do you get the P-type? It is through doping silicon with group 3 elements. If previously you dope it with group 5 elements having excess electrons, now you're going to dope it with group 3 elements. Example is gallium. Okay, in P-type doping, boron or gallium is used as the dopant. Yeah, these elements each have 3 electrons in their outer orbitals. When they are mixed with the silicon lattice, they form holes. Holes means empty. Yeah, they form holes in the valence band of silicon atoms. This means with the presence of these holes, electrons in the valence band can become mobile. Electrons in this valence band can hop onto this hole and move. Yeah. So this level, the acceptor level, if previously you talk about the donor level, now we're talking about the acceptor level in the P-type. The acceptor level is very, very close to the valence band, making the electrons in the valence band easy to move onto the acceptor level of the P-type semiconductor, or the holes, yeah, the holes, so they can move. The holes will move in the opposite direction of the movement of electrons. If the electrons flow that way, the holes flow the other way, obviously, because the electrons are hopping, are using these holes to move around. So the holes are seen to move the other way. Yeah. Because the dopant is fixed in the crystal lattice, only the positive charges can move. Due to the positive holes, these semiconductors are known as the P-type, or P-conductive, or P-doped, positive type. Yeah, there's a lack of electron because gallium is from group 3, not enough electron to sit with the silicon here, positively charged. Yeah. So there is a question here. The following questions are based on crystal defects and band theory of metals. Differentiate between a stoichiometric and non-stoichiometric crystal defect in ionic solid. This is from my previous lecture. Give an example of each one of them. So use this question to test your understanding of my lecture number 13, question 2, D2, doping semiconducting elements with impurities improves their electrical conductivity. Explain this process, either N-type or P-type semiconductor. So like what I explained earlier. And number 3, draw a representation of a band gap of germanium and selenium and discuss any difference between them. To understand, to know what does the question want, or for question D3, look at the position of germanium and look at the position of selenium in periodic table. Germanium is a metal, is a semiconductor because it sits on the metalloid area, and selenium is definitely non-metal. It is an insulator. So use this fact to explain. I'm going to discuss. Oh, yeah. The answer will be discussed in the class when I meet you next. So that is my lecture number 14. It takes 56 minutes and it is on the metallic bonding, band theory of metals, and semiconductors. I hope this lecture will explain to you clearly what these topics are, and I hope you're going to get a good understanding of the whole thing. So thank you very much. I will see you in class and also in my next lecture, lecture number 15. Bye, Assalamualaikum, and take care. Keep safe, everyone. Bye-bye.